Imagine a night with the sky filled with vibrant shades of green, blue and red. These dancing lights, known as the aurora borealis or northern lights, have captivated humanity for centuries. But have you ever wondered what causes these mesmerizing displays? The aurora borealis occurs in the high-latitude regions of the northern hemisphere. Its southern counterpart, the aurora australis, graces the skies of the southern hemisphere. Thanks to scientific research, we understand the science behind this captivating phenomenon. Let's dive into the heart of this cosmic dance and uncover the secrets behind the aurora borealis. The aurora borealis is a fascinating example of the interaction between the sun and the earth. This natural phenomenon, also known as the northern lights, has enchanted humanity for centuries with its vibrant colors and mesmerizing movements. This celestial ballet is orchestrated by charged particles from the sun, guided by the Earth's magnetic field. When these particles collide with gases in the Earth's atmosphere, they emit light, creating the dazzling displays we see in the night sky. The sun, a giant ball of hot electrically charged gas called plasma, releases a continuous stream of charged particles known as the solar wind. This solar wind is mainly made up of electrons and protons that travel at high speeds through space. As this stream approaches Earth, it encounters Earth's magnetic field, a protective shield that deflects most of the solar wind. This magnetic field is crucial for protecting our planet from the harmful effects of these solar particles. However, some particles are captured by the magnetic field lines and guided towards the polar regions, where the magic of the aurora borealis unfolds. Here, the particles interact with oxygen and nitrogen in the atmosphere, resulting in a dance of green, red, blue and violet lights that illuminate the sky. The sun is a dynamic celestial body, constantly releasing enormous amounts of energy into space. This energy manifests in various forms, including light, heat, and charged particles. One of these processes is the solar wind, a continuous stream of charged particles flowing from the sun's upper atmosphere, known as the corona. These particles are mainly protons and electrons, which are accelerated to high speeds. The solar wind travels at incredibly high speeds, reaching Earth in a matter of days. The average speed of the solar wind is about 400 kilometers per second, but it can vary depending on solar activity. As it travels through space, it carries the sun's magnetic field, known as the interplanetary magnetic field, IMF. This magnetic field is crucial for how the solar wind interacts with other celestial bodies. The IMF influences the interaction between the solar wind and Earth's magnetic field, shaping the intensity and location of auroral displays. Auroras, also known as the northern and southern lights, are a stunning visual spectacle caused by these interactions. The solar wind is a testament to the immense power of the sun and its constant influence on our planet. It not only affects Earth, but also has a significant impact on the entire solar system, influencing space weather and conditions on other planets. The Earth's magnetic field is an invisible shield that protects us from the solar wind. Generated by the movement of molten iron in the Earth's core, it forms a protective bubble called the magnetosphere. Some charged particles penetrate the magnetosphere, especially in the polar regions where the magnetic field lines converge. These particles collide with atoms and molecules in the Earth's atmosphere, releasing energy in the form of light, which we perceive as the aurora borealis. During periods of intense solar activity, such as solar flares, the solar wind becomes more energetic, intensifying the auroral displays. The vibrant colors of the aurora borealis result from the interaction between charged particles from the sun and the Earth's atmosphere. These particles, known as the solar wind, are ejected from the solar corona and travel through space until they encounter the Earth's magnetic field. When these particles collide with atmospheric gases, they transfer energy, causing the gases to emit light. This process is similar to what happens in fluorescent lamps, where energy is converted into visible light. The most common color observed is green, produced by excited oxygen atoms at an altitude of about 100 kilometers. This green glow is often seen at higher latitudes, where the concentration of oxygen is greater. Red auroras are produced by oxygen atoms at higher altitudes, usually above 200 kilometers. These auroras are rarer and can be seen on very clear dark nights, while blue and purple auroras are produced by excited nitrogen molecules. These colors are less common and usually appear at lower altitudes where the concentration of nitrogen is higher. The specific color emitted depends on the type of gas and the energy level involved. Oxygen and nitrogen are primarily responsible for the colors, but other gases can also contribute to subtle variations. The intensity and color variations in auroras are influenced by factors like the energy and density of the solar wind and the composition of Earth's atmosphere. Furthermore, solar activity, such as solar flares and coronal mass ejections, can dramatically increase the intensity of auroras, creating even more impressive light shows. And so, we come to the end of our journey through the aurora borealis, a true spectacle of nature. Let's recap some important points we've seen on this trip. We explored the mesmerizing dance of colors that paints the night sky, a show orchestrated by the interaction of solar winds with the Earth's magnetic field. We dove into the science behind this spectacle, understanding how particles coming from the sun, just imagine, collide with the gases in our atmosphere and give rise to vibrant shades of green, red, blue, and purple. And we didn't stop there. We unveiled the incredible journey that solar winds make, traveling millions of kilometers to reach our planet, guided by the Earth's magnetic field like a GPS. And to top it off, we discovered how each type of gas at different altitudes contributes to the variety of colors we see in the auroras. Thanks for embarking on this illuminated adventure with us, unraveling the mysteries of the aurora borealis. If you enjoyed the video, give it a thumbs up and subscribe to the channel so you don't miss the next expeditions. Oh, and don't forget to turn on the notification bell to stay updated. Your support is what motivates us to continue producing interesting and educational content for you. Until next time, and keep looking at the sky, always marveling at the wonders of our universe. Thanks for watching.